Okay, we are ready for problem solving. The first problem is this reaction spontaneous at room temperature 25 degrees Celsius. It's a combustion, delta H of reaction is provided, and then standard entropy is given. So let's just calculate delta S first. Delta S of reaction is simply sum of entropy of products minus sum of entropy of reactants. So product, I have carbon dioxide 213.6 plus 2 H2O molecules, 2 times 171, minus my reactants, which is 186 for methane, and then plus 2 times 205. So when we do this, we get negative 40.4. Entropy is decreasing, you're becoming more ordered, and if you look at it from 3 particles of gas, you're turning into 3 particles of gas. But this time, if based on calculations, entropy is decreasing. Now put the units, joules per mole per Kelvin. The first mistake my students usually make is not converting this into kilojoules. So this becomes minus 0.0404 kilojoule by moving it 3 decimal places to the left, or divide by 1000. Then Gibbs free energy is delta G is equal to delta H enthalpy minus temperature in absolute value times delta S entropy. Let's substitute. This is the case that this is exo and this is minus. Now minus times minus is positive. We are hoping this quantity is smaller than this, so delta G becomes negative. So we have minus 890 kilojoules per mole for that. Minus temperature is 298. This is the second mistake if you don't convert it to Kelvin. Times 0.0404. This quantity is very small compared to that, and you still get a negative value, minus 878. Units are kilojoules per mole for delta G, and this is indication that you are spontaneous at room temperature. So combustion is spontaneous, and we can prove it based on numbers. The second problem is you are breaking a covalent bond into 2 atoms of hydrogen. It's endothermic, and then we want to know if this reaction is spontaneous at 25 room temperature. If not, at what temperature it becomes. Now also, if you look at entropy, you're going from 1 molecule of H2 to 2 particles of H, therefore delta S should become positive. So let's just calculate it and see if that's the case. Sum of S of products minus sum of S of reactants. 2 hydrogen, 2 times 115 minus 130.6, and this becomes positive 99.5 joules per mole per Kelvin. So it was positive, so our estimate was right. Now let's just divide it by 1000. So delta S is positive 0.0995 kilojoules per mole per degree Kelvin. Let's plug it into our delta G equals delta H minus T delta S. So this is the case that this is positive and this is also positive. Now remember, this at high temperature, this becomes a larger quantity of negative and overwhelmed, so we want temperature to be high. Let's see if 25 is high enough for that. So we plug in the numbers, positive 436 minus temperature is 298 times a positive 0.0995. Unfortunately, this is a smaller quantity, and it's going to be positive 406 kilojoule per mole. So our conclusion is non-spontaneous at the given temperature at 25 degrees Celsius. Now let's find the temperature that it becomes equilibrium, and then let's increase it. When delta G is equal to 0, that's when delta H minus T delta S is equal to 0. And this temperature has a specific name. It's known as equilibrium. So we can calculate that. So TEQ for equilibrium is simply delta H over delta S. And that's our minimum temperature. You have to increase your temperature beyond this point. So this is equal to our delta H, which is 436. I use this, divided by our delta S, which is 0.0995. We get a very large number, which is 4,386 Kelvin. If you subtract 273, you get in Celsius 4,113 degrees Celsius. So it will say, look, temperature should go above this temperature. You have to increase the temperature, then delta G becomes negative. So we are going to say T of reaction, temperature of the reaction, should be greater than T equilibrium, which is 4,113 degrees Celsius, for reaction to become spontaneous. So sometimes you have to calculate the temperature, the minimum temperature, and increase it or decrease it. The next case, hopefully, is a decrease of temperature. Let's look at this case scenario. Is this reaction spontaneous at room temperature? Now, this is liquid water turning into solid ice. At room temperature, it shouldn't take place. But you agree this is exothermic. A tiny amount of kilojoules is coming to life. And since you're going from liquid to solid, you become more ordered. Delta S should also be negative. Let's see if that's the case. So delta S of the reaction, sum of S of products minus sum of entropy of reactants is 48, take away 70, and it's definitely negative. So our guess was good. So this is negative 22 joules per mole per Kelvin. Let's convert it to kilojoules. So delta S is minus 0.022 kilojoule per mole per Kelvin. Let's plug it into the delta G, Gibbs free energy, and see if we get negative or positive. Now remember, this is the case that you are exo and delta S is negative, you're becoming ordered. Now negative times negative, this makes it a positive quantity. We are hoping this is smaller than this. If not, the temperature has to cool down. So negative 10 degrees might be our case. So let's just plug it into the temperature given. So delta H is minus 6.01 minus 298 times minus 0.022. When you do this, you get a tiny positive value, but still positive. And this is indication that you are non-spontaneous at room temperature, at 25 degrees Celsius. Let's cool the temperature to negative 10. You should become solidified, because 0 is probably equilibrium temperature for that at atmospheric pressure. So delta G for new condition, delta G of this reaction at negative 10 degrees Celsius is equal to same delta H minus 6.01 minus the temperature now becomes 273, added to this becomes 263 Kelvin. Then again, Kelvin is always positive. We don't have negative Kelvin. It's absolute. 263 times our delta S, which is minus 0.022. When you do this, then you get a negative value. You get negative 0.0224 kilojoules per mole. And this negative is a sign or indication that you are spontaneous at negative 10 degrees Celsius. Liquid water turns into ice at negative 10 degrees Celsius.